Too sharp.
Yeah.
All right, so thanks for coming. So today you're pleased to have Eero Räty from Sweden. You stay here for more than 4 months, right? Just until June 4th.
Yeah.
And we'll talk about discrepancy, eigenvalues in MaxCut. Please.
Yeah, thank you, and thank you for the invitation to come here as a guest for a few months and the opportunity to speak with you. So this is joint work with Benny Surakov from ETH and Iswan Tomon, who is my colleague in Umeå University, Sweden. So let me just start with a brief background. So what is discrepancy? So as a sort of a more general concept, discrepancy measures the deviation from the expectation among substructures. So there are plenty of examples of discrepancy-related problems in combinatorial geometry, which are of specific interest. The work I'm about to talk today is not quite related to them, so it's related to very specific concept of graph discrepancy. But some sort of ideas behind them are of similar nature. As some other examples, so what I'm going to be mostly talking about is positive discrepancy, so it's slightly different from the usual one. So in the usual one you don't care about whether you deviate from the expectation more or less, so from the positive side or from the negative side, whereas here the distinction is made. A kind of a particular example of similar flavor is perhaps Roth's theorem on 3 APs. So one way to prove it is to assume that you don't have 3 APs in your set. Then as an intermediate step you prove that there is quite a long sub-AP which has a strictly larger density than your original set, which allows you to do a certain density increment argument. That's kind of same as saying that the certain sub-AP has a large positive discrepancy. It's going to be very similar to that. So let me start defining what this graph discrepancy actually is that I'm going to talk about. So given a graph G, I'll write n for the number of vertices, m for the number of edges, p for its edge density, so m divided by n choose 2, and d is the average degree. So d is defined as p times n minus 1. Sometimes we restrict our attention to actually regular graphs, in which case this d is just the regularity of the graph. So now given a subset U of the vertex set, define the discrepancy of U to be number of edges in U minus p times the size of U choose 2, where the second term is just the expected number of edges you would see inside a set of size U if this graph were random, which density p. So this is really how much does the number of edges in U deviate from the expectation. And then we define the discrepancy of a graph G to be the maximum of the absolute value of the discrepancies of the set. So a natural question to ask is that how small then can this quantity be? Obviously under some constraints. A natural constraint is given the edge density of G. So let Fp of n be the minimum of discrepancy of G, given that G has density P. So in 71, Räty and Spencer proved that when P equals half, this is more or less n to the 3 halves. So the crucial bit here is to prove the lower bound. The upper bound follows by considering random graphs, because random graphs has the maximum and the minimum of this quantity are going to be n to the 3 half with high probability. Then quite a bit later, this was extended to other densities. By Räty, Goldberg, Bach, and Spencer, who proved that again it's the random graph which does the best. So I rather write root dn than root p times n to the 3 halves. Subsequently, but let me just now remind that this is really a function of p and n in this way. And these two conditions shouldn't be sort of deemed as too restrictive. If you think about graphs of density 1 over n, it's basically you're already hitting like 3 regime. Like you have n edges here, so it's really, really sparse graphs we are talking about. And here it's the same as like we are at a very dense regime. So they are kind of uninteresting in some sense. Also, one sort of a trivial observation is that the graph and its complement have the same discrepancy. So we can assume that, say, the density is always at most half to avoid this perhaps a bit more unnatural regime where P is 1 minus a little bit rather than B being really tiny, which is, at least for me, easier to visualize. Okay, so is this the end of the story? Because we have basically determined the growth speed. Gladly not, because we can look for this one-sided quantities. So define the positive discrepancy of G to be simply the maximum of the discrepancies, and the negative discrepancy to be the minimum of them, but with the sign flipped. So these results show that at least one of them is large, but the more interesting question now is that what can we say about the smaller one? Can we prove some non-trivial lower bounds for it? So in 2006, Bolovas and Scott essentially proved that if you are close to satisfying this quantity, if your discrepancy is close to being this small, then actually both of them, these must be of this magnitude. or to put it, or also if one of them is substantially smaller than this one, the other one has to be much, much larger than that one in a multiplicative sense. So they prove their product is always at least dn squared. And again, under this additional assumption here, actually I want to write 1/2 because then I avoid writing down this annoying 1 minus b over n term, which is kind of taking out very dense graphs. Yes, sorry, here it should also be 1/2. Essentially because, of course, we will have a similar contribution from those graphs whose complement is very sparse. They have also rather small discrepancy for obvious reasons. So in particular, it follows that both of them are at least linear. So can they be linear? They can be linear. So if G is a disjoint union of cliques, how do we minimize the negative discrepancy? So if we have a set of a given size, we sort of ought to choose equal number of vertices from each of these blocks. Now do some optimization. It turns out to be the best to choose 1/2 from each one. Do some annoying calculations. You'll see that the negative discrepancy is going to be linear. Also, a trivial observation. The positive discrepancy of G is the negative discrepancy of G complement. Hence, so this guy has negative discrepancy linear, and similarly, the positive discrepancy of Turan graphs is linear. Can we tweak this construction? Can we put different sizes for these cliques? No. Why is that the case? Because again, to sort of minimize the negative discrepancy, one ought to pick a subset of the same size. But now the density of the subgraph is going to be 1/r, but if you substantially vertebrate these sizes, the density of the host graph is going to be less than 1/r. So here you are subtracting 1/r times you choose to from 1/r minus delta times you choose to. So you actually get a large negative discrepancy. So this really only works if these sizes are equal, or more precisely close to being equal. So essentially we have these configurations only for quite a sparse set of densities. So for positive discrepancy, this only works for densities which are of the form 1 minus 1 divided by r, and for negative discrepancy, we have this only for densities which are of the form 1/r. So it's natural to ask, could we improve these results for other densities? So already much earlier, although phrased in a slightly different language, Alon proved that if G is irregular and the graph is really sparse, then the positive discrepancy of G is at least as large as the one of the random graph. For the proof to carry over, one needs some sort of a sparsity condition because it's a probabilistic argument based on having certain edges chosen sufficiently far away from each other, so you need the diameter of G to be quite large. So in part,
what is the exponent?
it's 1 over 9.
Okay, thank you.
Yes, thank you. The exact value is not terribly important. It's just that it's n to some rather small number, not 1/3 or 1/2, and certainly not linear. So, motivated by sort of the lack of good configurations elsewhere, Vertret conjectured that if P is epsilon far away from all these Turan densities, and also P is far away from 1, then the positive discrepancy should be minimized for the random graph. Okay, so there are some other words mentioned in the title, MaxCut and eigenvalues of the graphs. So let me now briefly tell about them as well. So MaxCut of G is just the maximum number of edges between U and its complement, where we range over all the possible subset of U. So if you have a graph over here, we partition it somehow into two parts, and we count what's the number of edges going across. So a probabilistic of the first order method gives us that there is a cutoff size at least m/2. So define the surplus of G to be MaxCut minus this one, just to sort of scale it appropriately or shift it appropriately. So in 75, Edwards proved that if the number of edges in G is m, then the surplus of G is at least constant times square root of m. He actually proved an exact function in M, which is a title of a bound for cliques of size, I think, or a number of vertices. But this asymptotic bound, it's quite easy to see that any disjoint union of cliques match it up to this multiplicative constant. We can also perturbate this graph a bit, so we can essentially for both the discrepancy and MaxCut or surplus, if you pick two graphs whose symmetric difference is small, then as long as that small is smaller than the maximum of the positive discrepancies or the surpluses, then they have the same asymptotic order of them. So we could sort of change these pictures a little bit. For the surplus question, we now could have cliques of distinct sizes as well, because here we are really taking a partition of the vertex set into two halves. So here it's optimal to just slice each of these cliques into two equal size halves, and then when just the number of edges matters, it basically doesn't matter as much how large these cliques are. So there's a bit of a difference between these problems. So this conjecture was kind of motivated from the observation that we have this trivial lower bound, which is tight in certain instances. Can we improve the lower bound if we substantially deviate from this trivial example? So here the same question was asked by Eero Räty. What happens if we force ourselves from this sort of collection of near extremal configurations? So the area of interest became studying the size of the surplus of the MaxCut under the further assumption that the host graph G is H-free for some graph H. So Alon, Volodash, Krivlevich, and Sudakov, three proved that if G is H-free, then this surplus is actually at least m to the half plus epsilon h. And there has been some recent development for certain choices of h. I think the conjecture here is that the exponent should be as large as 3/4 for every h, but if I now remember correctly, it's not even known that there is a uniform lower bound.
This is induced H-free or just H?
Just H-free. And how does this relate to discrepancy? Well, if G is deregular, then the surplus matches with the negative discrepancy up to a multiplicative constant. So bounds on negative discrepancy imply bounds on surplus and vice versa. There is also a notion called sparse cuts, but there one has to be a bit sort of more careful. The reason is that you can't define it as a minimum, because otherwise you just take empty set and the whole vertex set, and that has 0 edges between. So you have to restrict to half size cuts, and that's also equals positive discrepancy up to a multiplicative constant. So results on positive discrepancy imply results on this sparse cut problem as well. Okay, so finally it's time for the eigenvalues. So now we assume that G is irregular. A is the adjacency matrix of G. And lambda 1 up to lambda n are its eigenvalues. And u1 up to un are the respective eigenvectors. So because it's deregular, we know that the largest eigenvalue is d, and the corresponding eigenvector is the all-one vector. How does this correspond to discrepancy? So an implication of expander mixing lemma states that for any u, the number of edges inside of u minus the p times u choose 2 is at most lambda 2 times u plus d. So we conclude that the positive discrepancy is upper bounded by lambda 2 times n plus term that is linear in n. So if we can get away from the linear regime, this is going to be small compared to the positive discrepancy. So essentially lambda 2 is lower bounded by positive discrepancy divided by n. Well, as some of you may be aware, there are very few examples essentially Turan graphs for irregular graphs where lambda 2 is 0. So adding this linear term is just sort of taking care of those instances, and that's not the main thing here. So essentially bounds for positive discrepancy, lower bounds for positive discrepancy would imply lower bounds for lambda 2. So what's known for lambda 2? So Alon-Boppana theorem states that if the diameter of G is at least 4, then lambda 2 is at least multiplicative constant times square root of D. Unfortunately, the proof sort of completely breaks down if the diameter is 2 or 3, so we don't get any sort of information regarding lambda 2, and that can already happen for quite small d, even when d is of the order n to the 1/3. Basically because then the second neighborhood could have size n to the 2/3 and the third neighborhood could cover the whole graph. So so Alon-Boppana is sort of there are some quite sparse graphs already where we don't know anything about the second eigenvalue. Okay, so together with Benny and Istvan, our sort of aim was to find lower bounds for positive discrepancy, because while the quite ambitious conjecture was to sort of prove that the random graph is the best, we sort of thought that substantial improvement for the trivial linear lower bound would already be quite interesting. So something that is something depending on d or n, which is tends to infinity times n, would already be interesting when p is bounded away from these Soran densities. And we managed to obtain such a result for when b is less than half minus epsilon times n. So the minimum of positive discrepancy of G when G has average degree is so it's minimized by the random graph if D is less than n to the 2/3. So remember that Alon proved it for n to the 1/9 under the regularity assumption. So we managed to push down the upper bound quite a bit. Then something weird happens. So it actually starts decreasing in this regime, and it's tight. Then our upper bound still remains true, but we don't have a matching lower bound construction. Our lower bound remains true, but we don't have a matching upper bound construction. And this upper bound is true for any d, but obviously when d approaches linear regime, this becomes linear, so it becomes uninteresting. So we kind of want to get a better bound, something which is kind of has a positive dependence on d times n, and we managed to get to 1. And here we don't have a matching upper bound either. So in particle, the strong form of the vertices conjecture is actually false. So there are graphs beating the random one. But it's true for graphs of average degree less than half minus epsilon n that the linear lower bound can be improved. So our contribution was purely on the lower bounds. The upper bounds we found from the existing literature. So there exists strongly regular graph with d equals n to the 3/4 and positive discrepancy being n squared over d. In fact, it has the second eigenvalue also n divided by d. So hence our lower bound together with this bound forces the positive discrepancy to be n squared divided by d. And then to extend to all the values in this regime, we just take random sparsification of this graph, so random induced subgraphs. And it's a sort of, one has to be a bit careful, but essentially Cauchy interlacing provides that the second eigenvalue still scales like n over d, and hence the positive discrepancy also scales like n over d, or n squared divided by d. So that provides us a matching upper and lower bound.
Is this basically the only counterexample that you know to? This is a counterexample to Weierstrass conjecture, or did I misunderstand something?
So there is for linear size. So if d is n over p, where p is a prime at least 3, there exists graphs GP with positive discrepancy n to the 4/3, which beats the random bound as well.
Okay.
And we believe that this is the correct for linear.
Right.
So we believe that here the exponent should be 1/3 rather than 1/4, and of course we believe that this log n term could be removed. That's not quite the end of the story, so I think I'll go back to it at the end if I have time. But there's a stronger form of this conjecture, which is that, okay, now suppose that your graph has a symmetric difference, at least epsilon n squared, to a Turan graph. Then there are actually examples where we have 4/5 instead of 4/3. So it's even smaller than that. But they have density half, or that graph has density half plus little over terms. So it's technically doesn't fit this sort of basic version of the conjecture. So for eigenvalues, we would just get similar bounds, but actually they can, towards the end, they can be a bit improved. So
do you want d greater than or equal to 1 or 0 in the first region?
here,
Yes.
it's 1. So basically average degree is greater than 1. So we forbid graphs that have only linear number of we don't want graphs that are sparser than 3. So I think here we could add any constant, but we don't want sort of graphs that have density little o n. So little o n edges. Because then in that case it's actually, I think you can come up with some very ad hoc arguments to determine exactly the positive and negative discrepancies basically by using the fact that there are many isolated vertices and so on. But it's basically putting one there is just to make sure that we are in an interesting situation. So for second eigenvalues, we have to restrict ourselves to regular graphs. So among d regular graphs, we get that second eigenvalue is at least square root of d in the same regime. Then it's at least n over d, and both of these are right. Not quite. Well, upper bound is tight for n to the 3/4 because it's a stronger graph, so it's regular. But here, to prove the tightness, we take random falsification, so we might lose the regularity. So there are examples of graphs with this average degrees, which have a matching second eigenvalue. Maybe it would be possible to sort of work out the details and modify them to make them regular, but we didn't bother. Construction. Not quite regular. And then here, we get d to the 1/3. Oh, but I forgot the most important thing. This is a theorem of Eero Räty and the rest of us. So Eero Räty had proved basically this last one by much more complicated methods earlier, and we found substantially simpler proofs, and I think if you adapt his methods, it could be possible to obtain these two other bounds as well. And also what we proved and he proved originally is that in this regime, so whenever d is less than half minus epsilon n, lambda 2 has a sort of a positive dependence on lambda n, which is perhaps a bit surprising. So lambda 2 grows like at least a square root of lambda n. So in particular, if you have a d-regular bipartite graph, then the eigenvalue is at least root d. That's constant. So observe that the Bolova-Scott theorem gives you that lambda 2 times lambda n is at least omega d. So that together with this one automatically gives you this d to the 1/3 bound. Okay, so any questions so far? Before I move to sort of briefly outlining one of the proofs of these results. Okay, so I heard that some of you watched the seminar given by Istvan to Oxford where he discussed some of the earlier bounds. So I was planning to go through a sketch proof of this last part where I don't quite get d to the 1/4 times n, but I get a worst bound, which is still beats the linear lower bound in n, and kind of demonstrates the main techniques behind the more complicated one. And the proof is perhaps surprisingly purely algebraic. So this is a very combinatorial problem, and what we essentially did was that we used a tool called graph Grothendieck's inequality, which is a result proved by Alon and some others in early 2000, which generalizes an old inequality of Grothendieck to a graph setup, where we essentially found a semi-definite relaxation of the positive discrepancy and translated this problem to a question which purely deals with matrices and their Frobenius inner products. So the first observation is that the positive discrepancy, written as a kind of an optimization problem, is given as follows. So we pick a 0, 1 vector, which is the characteristic vector of our set U, and this is exactly the number of edges, and this is the expectation term. The trick to observe here is that we can actually replace this discrete set of 2 points with a continuous interval. And the reason is that if we fix all but one variables, then this is going to be a linear function in the last variable, so it always achieves its maximum at one of the endpoints. So this maximization problem over this cube 0, 1 to the n, the optimal point occurs at a vector where every coordinate is 0 or 1. A bit trickier observation is that after a multiplicative constant, we can change this to the interval from -1 to 1. So it's a bit non-obvious. Again, the same argument implies that this is really the interval from the discrete of -1 to 1, and that's going to be quite useful because then this is going to give us U complement and U, and essentially if this is large, then either the positive discrepancy of U or U complement is going to be large, but we lose some multiplicative constants in the process, but I'll not discuss it further. Why is this a useful observation? Well, it's useful because that allows us to translate it, use the semi-definite relaxation. I'll just erase this. Just to get the names right. So in 2006, Alon, Makarychev and Naur proved that if beta, so if A is a symmetric n by n matrix, and beta is the maximum over xi's taken from the interval from -1 to 1 of aij, xi, xj. Essentially the situation we have here with applied to the matrix A minus P times J minus A, which is symmetric. And beta star is the semi-definite relaxation of it. So we pick a vector to represent each x, which has L2 norm at most 1. And the products xi, xj are replaced with inner products. Then we trivially have that beta star is greater than beta because we could pick all of these vectors to be one-dimensional and the first coordinate to be xi. But the crucial part is that beta is lower bounded by constant times beta star divided by log n. So the original growth index inequality is basically a bipartite graph variant of this. And there one doesn't have this log n factor. So what Alon and others observed is that one can adjust the proof and combine it with some combinatorial insights to get a variant that applies for every graph with the expense of adding a multiplicative log n factor. So how does this help us? So we can now use the semi-definite relaxation to lower bound positive discrepancy. So we write for matrices A is greater than B if and only if A minus B is positive semi-definite. And we defined an optimization problem P disc of G to be the maximum taken over matrices X, which are positive semi-definite and whose diagonal entries are at most 1 of X, the inner product of X and A minus Dn times G, where this Frobenius inner product is just a trace of AB transpose. So it's the sum of AIJ, BIJ. So we multiply the air entries and sum them up. So here X is the gram matrix of these vectors. So because they have L2 norm at most 1, the diagonal entries are going to be at most 1, which motivates this condition, and gram matrices are going to be positive semi-definite. So to avoid working with these vectors, we just widen the, we just take this problem where we actually look for the maximum over positive semi-definite matrices, which diagonal entry is less than 1, which is going to be equivalent to it. So, and some eagle-eyed viewers might notice that here I have simplified the expression a bit, so I've got rid of this minus I term. It's easy to see that those things only matter the linear terms, so this is really going to be fine. So now the question is that how do we cook up a suitable matrix that is going to give us an improved lower bound? So let Y be the matrix, which is A squared minus D squared n J. So this is chosen so that the sum of the entries of, so okay, so now I'm assuming that G is D regular. Just for make the technicalities easier. So because G is D regular, the O1 vector is going to be an eigenvector of A, and this is going to be, so its eigenvalue is going to be D squared, and this J divided by N basically is the V1 transpose matrix. So the Frobenius inner product of Y and J is going to be 0. So this is also why I'm dividing by D. I'm dividing by D because the diagonal entries of a D regular matrix A squared are just D's. So now I'm making the diagonal entries 1, and I'm subtracting something small from them. So this matrix satisfies the conditions of the optimization problem. So the inner product of y and a, well, if you just did the maths, then you would find out that essentially we can decompose a also as a sum of lambda j times ui transpose, and the cross terms kind of contribute 0. So what we get is just the sum of the lambda cubes, which is 6 times the number of triangles minus d cubed. So, if we have many triangles, we get large positive discrepancy, because this is a lower bound for p-disc, which is a lower bound for positive discrepancy. In fact, there are other methods. So, observation 1. And note that this d cubed is just the expected number of triangles one would expect to see in a random graph. So this kind of relates the triangle count and the discrepancy problem as well. Fact which I'm not going to really explain further is that other methods actually can be used to cover arguments where this is just a little bit smaller than d cubed. So if number of triangles minus d cubed is much greater than minus d to the 3 halves times n, then we are still sort of safe. So if it's sort of within the margin of error from the number of triangles, there are some other arguments that can be used to prove it. This looks suspicious, but essentially what I want to demonstrate is that the other case where this is really small kind of corresponds to the case when this matrix Y actually gives you large negative discrepancy, because the negative discrepancy also has the same semi-definite relaxation. So now what our aim is to basically flip large negative discrepancy to large positive discrepancy, i.e. we assume that there is a matrix Y, which is this particle one, which because of a small triangle count demonstrate us a large negative discrepancy, then we can use it to get also a large positive discrepancy, kind of proving a inverse Bolobas-Scott theorem in a way that in this regime of densities there is a inverse relation, so the product of the one-sided discrepancies has to be large, but also if one of them is large, then the other one has to be large, which kind of bridges the gap and gives us a lower bound. So let delta be the number of triangles minus d cubed. So then this is the absolute value of delta, and assume that this is much less than 0. So we would like to flip the sign and get something positive out of it. So let us consider a matrix Y Hadamard product minus A. So a matrix whose ij entry is minus Yij Aij. So, sure product theorem implies that if A and B are positive semi-definite, then the sure product is also positive semi-definite. But the inner product of these two is just minus the inner product of y and a. So this would be great because this would translate large negative discrepancy to large positive discrepancy. The problem is that minus a is not positive semi-definite. So instead, let us force it to be positive semi-definite. So here we choose matrix I just to ensure that we have some room to play with. We kill the largest eigenvalue, and the second largest eigenvalue is the one which is preventing us from being positive semi-definite, so we divide by lambda 2. And now it turns out that it's still this A term that dominates. So this is going to be the number of triangles divided by lambda 2 times d. So we get the lower bound for the positive discrepancy, which has an inverse dependence on lambda 2. And so now I'm running out of time, so basically how you could finish is that you get also a lower bound which has a positive dependence on lambda 2, and combine those together to actually improve the linear lower bound. But basically the aim was that we translated this problem to this semi-definite relaxation and made the observation that we can actually flip negative discrepancies to positive discrepancies by taking these Hadamard products. Anyway, I think I better stop here. It's getting half past. So thank you.
Okay, any questions?
So if you have a explicit construction that's pseudo-random but with extra more triangles than expected, can
Yes.
you just use it directly here?
So we have other arguments where. So basically, we had the 3 bounds. So the first 2 bounds, which apply in sparse regimes, they actually apply in dense regime as well if you have a larger triangle count than what you expect. So essentially, so if you saw the talk given by Eastman, then those vector approaches used, they actually rely on the number of triangles being large. So what you really care about is that this lambda delta being either positive or not too much negative, and then you can recover this square root d n bounds or n squared over d bounds. So what's really the problematic case is when the number of triangles is much less than the expected number, and then we just have to find a method to flip negative discrepancy to positive discrepancy. I mean, in this case we know that the negative discrepancy is large, and the large negative discrepancy is actually witnessed by this matrix Y, because the same semi-definite relaxation works for negative discrepancy as well. If that answers your question.
Well, my question is, given this observation, if you just want the instance of Y where this difference is really large, right? The number of triangles is larger than expected, which can then translate you, do I understand it correctly, to a lower bound on the positive discrepancy?
Yes, so if the number of triangles is large, you get a lower bound for positive discrepancy, but that's actually using a different method than what we are showing here.
Then my next question is, if I assume the graph is a KD graph, does it help you closing some gaps in one of those regimes that you don't have the matching bound, upper bound?
So there are some if I remember correctly, there are some results for Cayley, specifically for Cayley graphs that were proved by Conlon and Zhao some
Yeah.
years ago. Now I can't remember whether it was for eigenvalues or for positive or for the discrepancy.
They just prove for discrepancy, it's the same as the eigenvalue gap, also using Grothendieck's inequality.
Yes.
Yeah.
So I think their results were tight already. So I think the technicalities we used, I think they are not really. In certain cases, like when the graph is strongly regular, so there's a kind of a, when you look at the powers of A, so you have A and A squared and so on, then they start repeating, so you only have to consider A squared and J and I. Then some of the stuff here becomes substantially easier, and I think we can recover exact bounds. On the other hand, strongly regular graphs are pretty boring because the Bulova-Scott kind of automatically implies for them that the discrepancy is dictated by the eigenvalues. Oh, sorry, the one-sided discrepancies are dictated by the eigenvalues.
Any other questions? Yeah, if not, let's thank the speaker again.